Welcome everybody. I think the next guys don't really need an introduction. Let's present you Corona talk for the iPhone.
All right, I'm Joshua Hill. Probably know me as POSIX Ninja. I'm really happy to be here today with all 4 of the core members of, I guess, the Jailbreak Dream Team. I'm not sure who coined that word. Well, basically, we broken up the presentation into 2 parts. First part, we're going to cover iOS security basics, and then I'm going to cover the Raccoon format string attack, how we use that to gain the initial unsigned code execution. Then Cyril is going to be giving a talk on the HFS kernel exploit and how he managed to fuzz and find that. So, here's guys.
Yeah. Okay, hi. Well, we'll start with a small introduction to the security features of iOS. It's the operating system. iOS was introduced in 2007 with the release of the iPhone, and it was initially named iPhone OS 1.0 and later renamed after resolving the naming issue with Cisco, because they used it for their routers as the name for their operating system. And the current release is iOS 5.1.1, and iOS has undergone a large development process and has gained a lot of security features over time. So it has grown to a really well-secured operating system, and it's considered to be one of the most secured OSs around. So, yeah. The flaws that we use for jailbreaking are actually even each time more and more hard to find. And another point is that if we release a jailbreak, then it's really quick that Apple will push out a fix in form of a firmware update. And this is the problem that we each time when a new release comes out have to basically start from the beginning, because they closed all our holes we used to get into the system, and this every time quite a big challenge. So I'll start with the security features. The boot chain is the first part. It's all the firmware files that are used for starting the device have signature checks, and these signature checks prevent modifications of the firmware files to boot the system or change the kernel, patch whatever you have to do to maybe enter the system. And this is followed by code signing, which prevents modification of the binary that get executed. So if you try to patch a program, it will just not run because the signature doesn't match. The next part is data execution prevention. This is a feature that protects memory pages in a way that you can either write to this page or execute code from this page, but you cannot do both at the same time. ASLR is the next feature. This is designed in a way that the memory region for the libraries and also for programs is randomized. So basically you have a different address space for the libraries in use and for the program that is running. Then we have stack canaries. This is basically implemented by putting random values on the stack that are checked at the beginning of a function, and when the function is returning, then these values are compared to check for any stack manipulation. Partitions, this is very specific to the iPhone because we have the system partition, which is read-only usually, so you cannot change system files. And we have the user partition where all the data is stored, like photos or whatever. So this is a really clear separation. Then we have the users. This is actually not only root and mobile, there are more users, but so every process has a specific user it runs with, so to just prevent privileges that it doesn't need, we can exploit them. Another feature is sandboxing. This is a finer restriction for processes that prevents process from doing stuff like reading files or opening network connections, and so this is another step in the protection of the operating system. The boot chain can be exploited with the so-called line exploit. It is a heap overflow that allows code execution at the boot ROM level. It's a hardware exploit that cannot be just patched with a new firmware. This allows us to basically start the device with a custom RAM disk and a patch kernels and whatever you need to do with the device. And this is often the first entry point for so-called tethered jailbreak. This is a graphic showing the regular boot chain where we have the boot ROM, which authenticates the LLB, which then authenticates the iBoot, and then the next image, the kernel, is authenticated, and even the file system is also checked for any manipulation. If we now use the line exploit, we have basically we skip the signature checks and just load the patched images and can this way run a custom RAM disk. So we just lose all these authentication steps in the whole boot chain. For Corona, we have the first thing is we disable the address space layout randomization by just setting a specific launch D key so that on startup we just have this feature disabled. Code signing in this case is used by just running the original binary, which has of course a valid signature. This binary has a sandbox profile, but for some reason the entitlement section is not included in the signature checking, so we can patch the sandbox profile to actually break it and this way run this program but without any sandbox restrictions, so it can just like read any file or execute whatever we need to be done. Then Corona is loaded with a configuration profile that includes the so-called format string vulnerability. This is what Joss will present a bit later. And also the data execution prevention is then bypassed using ROP to achieve the next step of the exploiting. This is the HFS Plus vulnerability to actually exploit the kernel. This is what Cyril will present a bit later also. Yeah, for the A4 Corona, we had distributed that package for the Cydia packaging system. Since the Tether jailbreak was already present for quite a while, we decided to put all these this Corona setup into a Debian package for the Cydia system. You can just install this package, which will put the payloads in place and installs a copy that we patch of this Raccoon daemon, and then we'll execute it on startup. Okay.
All right. I'm going to cover the unsigned code execution and how we gain the initial actual jump into user land so we can get into the kernel exploit and be able to patch that out. Format strings in 2012, that's not really right. It was a short-lived bug, only around for maybe 2 years for the most part. There was really a lot of them. Not quite sure. I was pretty amazed when Cyril brought this to me because I had never got to work on a format string bug before. Basically, it shows the code of the bug. It was actually in the warning function and error function. So basically, any warnings or errors printed to the log would trigger this format string. YY warn calls into plogb. Plogb calls in plog common, which basically just reformats that. Well, it passed a variable argument function into here. It reformatted it into a string and then passed back the new format back into plogb, and then without even checking it, it just sends it to syslog or the terminal. Little basics on format strings. You can do lots of little neat things with them. You can use %sign_x. It'll print out the value in hex on the stack. If you put too many %sign_s's, it will actually try and dereference whatever address is there and print it out as a string. %sign_u, print it inside extra. Let's see, a couple weird things. If you put a number before it, it'll pad it so it's actually a longer length than it is. Because if you want zeros in the front. The $, it allows you to reference arguments on the stack relatively. So I guess 8 would reference the 8th argument stack. HH can make it only print 1 byte. And the most important one, %sign_in, actually writes the number of bytes printed so far onto whatever address is in stack. The old way they did it was they actually wrote the address they wanted in the format string and then referenced that back. But unfortunately, that way won't work anymore, because not only are the format strings actually copied into heap, and they're not actually on stack, so you can't reference them. But there is another way we can exploit it by using frame pointers. They're sort of like little linked lists on the stack. They basically hold hold stack pointers to allow stack unwinding. They're made on the stack in the prologue and prologue of each function. See, it's usually held in the register R7. You can see here pushing the old R7 onto stack. Then it moves the current stack pointer into R7. Of course, it allocates space for local variables. And then at the end of each function, it goes back, cleans up stack for us, and pops R7 and the return address, R7 the frame pointer, and return address back off the stack. And it kind of leaves this weird little pointers in the stack that all point to one another. But this is an example of the actual payload file included with Corona. See, we use %u, so that'll actually pad it out, whatever the number is. So 11u would pad it out 11 plus, well, 211 zeros. The next format string, it uses the relative offset one, which basically allows us to reach deep in the stack and use the variables very far away when we don't have to address them directly. Of course, then HHN, that basically means just to write the number printed, or the number of bytes printed so far onto the screen, which you have to kind of add a little extra onto there for the other format things added into there. But it would write 1 byte into whatever address was way far down stack. So basically, here's how we exploit it this way. Have an example, 1 frame pointer, 2 frame pointers, 3 frame pointers. Each one points to the next frame pointer. But if we're only writing 1 byte to it, then that frame pointer is going to point technically to the last byte in the address, since we're on a little Indian machine. So if we actually change that number to what we want, we can change this frame pointer to an address that's actually different. We can you can use basically overwrite this entire address to be whatever address we want it to be. And also, we don't need to know any solid addresses because we're just using addresses that are already on the stack and modifying them to basically allow us to write a payload of any size length. There are some conditions for this. The call stack has to be at least 3 functions deep. And you have to be able to execute multiple format strings in a row also, which we can do since it's in Y-warn, and there's plenty of call stack, or a very deep call stack in Raccoon. We have to use a ROT payload because on ARM, the arguments are actually passing registers, not on stack. So also there's data execution protection, like Cyril said. So we have to only use what code's available. We also have to bypass ASLR, which is not a problem in this one, but it can be done, and me and Cyril will explain how to do that at the talk after lunch break. But now, Cyril talk about the HFS kernel exploit.
Hello guys, I'm Cyril, also known as Pod2G, and I'm gonna talk about how we exploited the kernel in this jailbreak. So to do a jailbreak, you'll see that we need to patch the security features of it somehow. So basically, jailbreaking consists of removing certain features, security features of the kernel to let the user execute custom unsigned code. Yeah. Also, it adds the ability to run code outside of the container sandbox and not complying on App Store's application rules. This is a slide explaining the code signing basics, the mandatory code signing, because iOS kernel will refuse to execute unsigned code in different ways, because first, it won't let you load unsigned macOS. Also, it will refuse to load unsigned pages. So the first one is the kernel macro loader. The second one is in the handling of the memory. Also, the iOS kernel won't let the user map readable, and executable pages at the same time. This is not possible except for except that there is some special entitlement you can add to some processes to use the so-called just-in-time features. And Apple needs the JIT features for mobile Safari so that you can compete with Chrome on the Android platform, so that it's enough performance. So they had to modify a little their code to add this exception to their restrictions. And the guy, the well-known American guy, Charlie Miller, has found a hole in this process, and this JIT enforcement, and was able to execute code in a legit App Store application. But unfortunately, this is closed in 5.0.1. Also, the iOS kernel won't let you execute non-platform apps. I mean, the apps that are not distributed with the firmware outside of the container profile. This is another feature. So, now what? We want to execute unsigned code. So, what do we need to do to achieve this goal? Currently, the only public way to do so is to modify the kernel to avoid these security features, these code signing enforcements. The big problem with this is that the kernel is, you saw that previously, the kernel is authenticated by the iBoot with RSA certificates and such, so it's not really possible to modify it on disk. So we have to do it at the runtime in memory, because we don't have an exploit in the boot chain for an intercept. I mean, because at the boot, when limeren is not executed, we don't have an exploit in the boot chain, so we need to do it at runtime later when the kernel is loaded to patch these security features. What is nice about the kernel memory is that it's nearly all read, write, and execute. This is really interesting. You'll see that later. So, how to patch the kernel in memory? Yeah. A user process like Raccoon exploited with format strings can't do that because only the kernel can access kernel memory. So, to patch the kernel, you have to be the kernel. And thus, we need an exploit, a code execution exploit, to instruct the kernel to patch itself. So here is the vulnerability I found earlier in the HFS module. This is the changelog of iOS 5.1. So basically, there is an integer underflow in the handling of HFS catalog files. To be honest, I don't quite understand the bug, really. Yeah, I don't understand it. I just saw that it crashes the process when I try to mount. It crashed the kernel. Sorry, when I tried to mount a specific image that I modified. But I don't really understand the bug. I've walked into the source code of OS X anywhere and couldn't understand. This is quite complicated. So here is HFS Plus in figures. It appeared with Mac OS X 10.4. It supports for files up to 2 exponent 63 bytes. Was 2 exponent 31 bytes with previous HFS version. And file names can contain up to 255 Unicode characters. And it was 31 before. And was not Unicode also. Yeah, and there are 32 bit allocation block numbers, which means that we can access many more blocks than by the past. So here is the next. So because they changed the maximum block numbers, now we can access a bigger volume of 2 exponent 63 bytes at maximum. Also, the maximum files count was increased because of this, and also there's another feature that was added. One file can have multiple byte streams. I think any number of byte streams, but they don't use it right now. And it was 2 only by the past, only the data fork and the resource fork. So, talking about files, HFS Plus indexes are also files. There are 3 basic kind of them. The allocation file, which is a bitmap, the catalog file, which is a B-tree, and the extents overflow file, which is also a B-tree. There are other files as well, other standard files in HFS Plus as well. The attributes B-tree, the hot files B-tree, the startup file, but we won't mention them after. So, the allocation file is basically a map of all the blocks in the volume, and there is 1 bit per block. The bit is set if the block is allocated, that's all. It permits to the HFS engine to choose the right blocks, the right free blocks when you create a file. There's also the catalog file, which indexes all file names, file attributes, basic attributes, and up to 8 first extents. Extents is a sequence of blocks for consecutive blocks in the file system. So the catalog file is also B-tree. and he holds a parent-child relationship between folders and files. And the last one we'll talk about here is the extents overflow file, which is a B tree also, and which defines additional extents for files of more than 8 extents. Well, the bug happened in the volume header. You'll see that. That's why I'm talking about it. It defined the basic volume metadata of HFS, the version, the type, the block size, the number of blocks total, the number of free blocks. And also it points to the different index files in the volume. Here is one example. So, as you can see, the first bytes are H+, then there is the version that we can read after. And this is pointless to define each of the other values, because we are not really interested in this. But there are different four zones that define the standard default files. The allocation file, the extents file, catalog file, and attributes file. Here is the structure defining this area we can see. Okay? The first member of this structure is logical size of the fork. Then we have the clump size. I won't give you more details about that, because this is kind of complicated. The clump size, the extents, it's kind of complicated, so I won't give the much details about this. But one which is really interesting is the total blocks used by the fork. Then here is the idea. What if we modify the total number of blocks of the catalog file to be less than it really is? Like this. Let's see. We're going to try this on OS X 10.6.8. We'll create an HFS image using standard tools, DD, VN-Device, and new HFS tools. We'll mount it, add in some files, unmount, then we will patch this famous D word we saw previously, this one. And we will try this little mount sequence. We basically transform vn image.test to a block device, which is called dev vn0. Then we'll encode here the directory we want to mount, and we'll mount this image as a loopback device. Whoops! That crashes. I don't give the symbols of this panic, because it is pointless. I mean, it's different each try. You try it one time, it will crash in a specific function. You try it another time, it will crash in another function. It is random. So, this is random, so what does it mean, in fact? I also reversed a little the stack trace, and I saw that it happened a lot in Z-alloc and Z-free. So it has something to do with the heap, something like a memory corruption somehow. So after that, like I explained it earlier, I tried different things. I tried to connect to the virtual machine with KDP. I tried to do static analysis of the code of macOS 6. I really don't understand what it happens in the code. So shall I lose time on this? No, I'm going straight to exploitation. What tools do we have to help us understand this memory corruption? Hopefully, the zone allocator has debugging boot args. If you add -ZC to the boot args of the kernel, you have a special range that is done by a remove from zone, which is called by zalloc and z3, to check if the next free element is in the address space of the kernel or not. Also, we have the -zp boot argument that will just fill the whole freed memory with dead bits, which is interesting. So, adding these boot args helps the kernel to crash right on the overflow and not at random position. So this is kind of cool, I say. Also, there's one special feature that allows to send a core dump at right on the crash to a remote machine. This machine just have to have the kdumpd service running, and for the example, here is the command to do it in the operating system you want to test. Yeah, with these boot arguments, it's easier to understand what happens. We have the message over there. A freed zone element has been modified. Yeah, nice. And we have the full backtrace. So, we have coordinates, we have debugging boot arguments. Okay, GDB is now useful. So, you just need the kernel debug kits that are free and downloadable from Apple website, developer website. You just need the kernel, these symbol informations, and this little GDB script, kg macros, which is really useful. Here's the command to start GDB and source this macro utilities. Oh, sorry. So here is the symbolicated backtrace. Now we have the same symbols. We see that it happens in the HFS, in the mount HFS plus volume, and then it tries to search the tree, and it's bufferize the block, and it crash in zalloc. And one special cool feature of those KG macros is that you can do an after-death zprint that will show you the different heap zones, and the address. How to say that? In red. Okay. The address in red is the next free element of the zone that overflowed. So this address seems weird to me. Let's see. Here is the free block. Here is the free block. So because we added the ZP boot arg, it should be all dead bits here, and this is not the case. We have some parts of the image, of the HFS image, in the free block. So, yeah, this should be all dead bits, and the first and last D words should be the next free element of this chained list of free elements. Now, we can go even further with the heap debugging tools by adding zlog boot arg. Now that we know the compromised zone name, it's buff 496. Oh, I got that. I've not showed you. Anyway, this is not the point. We have the zone name. So now we can add this special boot arg that will trace allocations and freeze, which is really nice to know when you want to perform the Feng Shui. So here is the command to zlog the special zone. Now, okay, we know that we can overwrite a free element with custom data coming from the HFS image itself. So we have the complete trace of latest allocations and freeze with zstack debugging macro. I tried to play with this, but I concluded that buff 4096 bytes is not the best zone to play with, because it changes really often. Because also the root file system of iOS, for example, or OS X also use this special heap zone. So we'll see after that we need to change that zone to another one. One important thing also about iOS, which is different from OS X, I don't know why, but you can see the kernel heap, a Mageddon paper of Stefan Hesse. The next kernel page allocation is not predictable, while it is when your heap is defragmented on OS X. So I had to change the way to do this to achieve my goal. So, is it exploitable? We can write basically data to the next, to a free block in memory, a free heap element. And yeah, this is exploitable because this is a linked list, and if you can overwrite, and this is why it crashes also, if you can override the first D word of the next free element, and you can do 2 allocation after that, then this allocation happens in a controlled position. Yeah, as I said, we need to switch to a different zone. So to do that, I just modified the block size of my image to be 512 bytes. And we need to know the precise amount of allocations per mount and the precise amount of overwritten free blocks, overwritten elements of the heap at each mount. So here are numbers 3 and 5. Okay, so here is how we're going to exploit it. We have 3 images, one that is clean, the standard one, the original one, and another one that is the image that where we just have changed the famous D word I showed you previously, this so-called heap overflow image. Then we have a third image that is a payload to be written in the controllable location of the kernel. Here is the exploit sequence. We're gonna mount twice the first image, then unmount it, mount one time the overflow image, unmount it, and we'll need to mount the clean image one time again, then the payload image at last. So here is a table of a page in the kernel heap. You have in the first column the offset in the page, if it's allocated or not, and this is not quite related to the offsets. I should have put that elsewhere, but okay. This is the next free element list. So here is what happens when we try to mount the clean image. That you remember, it allocates three memory blocks. Here's the first block, the second one, and you can see the next free list is modified at the same time. Then the sequence VN image clean mount happening here. Okay. Then we will unmount these images so that we can control where the overflow happens. Okay. Okay, so next free element will be at offset 800 in X. We mount the clean image again. Oh, sorry, okay. I'm just confused, okay. Okay, we are there. Yeah, this is better. We mount the overflow image. 1 block, 2 block, 3 blocks. Then the overflow happens. And it overflows 5 blocks. And what is really interesting is that it overflows this last one, which is the next free element of the list. We unmount it. And again, we mount the clean image. See the overflowed element of the next free list here. There. We try to mount the VN image payload, and it is mounted in a position we control, because overflow data is controllable. Hopla. Exploit it. So, the idea now is to set the sysint address, the table of different syscalls, in this overflowed data, so that the first D word is this element points to a syscall we want, and what will happen is that we'll override the syscall table with our data. So we're pretty close to a kernel exploit here. What we have done next is to so basically we replaced the 512 bytes of the sysint with some controllable data, which is half sysint, half HFS, so that we can apply the HFS protocol rules on our image. Then we have replaced a particular syscall with a write anywhere gadget, and that write anywhere gadget that write anywhere syscall we have created is then utilized to restore the corrupted sysend and apply the jailbreak kernel patches. We just replaced one syscall with kernel write anywhere syscall that we then use in our ROP payloads to do the jailbreak. Here is the famous ROP gadget we used, QA for kernel write anywhere. It just takes the two parameters, which is the where we want to write and what we want to write, then store and returns. Okay, so if you need more information about this stuff, we are gonna release the source code of proof of concept after Hacking the Box publicly. And you can read, of course, the iOS Hacker's Handbook to know which patch to apply with the kernel write anywhere to do a jailbreak, which is out of scope here. Any question?
It must have been a challenge to develop the exploit on the actual iPhone.
Sorry?
Hi, here.
Where are you? Ah, okay.
Could you perhaps talk a little bit about the process you used?
Could you go up? Sorry, excuse me. It is kind of difficult for me to understand at this distance. Can you maybe take the mic, or you, Nikis?
Just continue with your question, please.
Okay. If you could perhaps explain a little bit about the process or the tools you use to develop on the iPhone, which is very hard to develop exploits on, seeing as debugging is very hard or impossible, and the migration from the Mac OS and into the iPhone.
So your question is, it's difficult to develop exploits directly on the iPhone, and what tools we use to develop these exploits. So, do you have any? He believes it's difficult to develop exploits directly on the iPhone because there's no debugging tools on the iPhone.
Of course, there are debugging tools on the iPhone. You can just use a serial cable and use the KDP protocol to remotely debug the kernel. So yeah, you have the right debugging tools to do exploits on iOS. This is not the point. The point is not about if we have the debugging tools or not. The point is that it's really difficult to write exploits on iOS because it's a really secured operating system. This is the point. Not right. Not quite the if we have debugging tools or not.
More questions?
Take it. Why?
Hi. I have to admit, we walked into this this presentation a bit later, so maybe we missed part. Not all of us have just such low-level knowledge. What I basically get is that you used an exploit in the HFS driver to gain access to to make the kernel execute privilege or access privileged memory. What I still missed is the part how you get the iPhone to how you get the kernel to boot with those different parameters, how to trigger it. When the chicken and the egg, that's the part I missed actually. Could you clarify that part, please?
Right. We'll actually be going over some of that part in the second part, the afternoon part of our talk. But the basic idea is that you can use LaunchDaemon's LaunchD to load a copy of Raccoon, which is signed by Apple, with an exploit configuration file, which will launch a ROP chain that then executes the kernel exploit. Does that make sense?
Right. And Raccoon has already been cleared by Apple then?
Sorry?
Raccoon was signed by Apple then?
Yes, Raccoon is the IPsec daemon for VPN on iOS, and it's signed and shipped on every iPhone.
That's the part I missed. Thank you.
Questions? No more questions? Well, then I'd like to thank you guys.